Hey guys, welcome again. Well, unfortunately, as Abby said, well, I send you the videos at the worst times possible. Well, here is the story. Well, not for for the time that I'm sending you the videos, but the problem is the following. It's impossible for me to cover everything in geometry. You realize that I should spend one semester doing all geometry, so I cannot do it. So I try to cover as much as I can in like a couple of lectures. Well, with that being said, unfortunately, today we're going to have a lecture and then I'll do a recitation on my own, or I'll send you an invitation for later on today to join the recitation, and I'll tell you what problems you should solve. But anyway, let's get started. Today, I will talk about vector geometry, and you'll see what that, in fact, let's call this geometry 2, lecture 3 prime. Okay. Oh, in fact, you know what? Let me continue from here. So that I will send you the okay. So we will talk about vector geometry. Right. And let's see what vector geometry is all about. We will see some applications of vector geometry. And you will see why we sometimes it's very useful to use vector geometry. In fact, I'll do a problem where I'll be stuck at some point using vector geometry. But anyway, we'll get there. But before that, I would like to do some theory. Let me, you know what a vector is. So basically, if I have the axis, right? The vectors are something like this, right? This is a u vector. We can have another vector, you can go like this, the v vector, and so on, right? You know, from calculus, you can add, you can subtract vectors, you can multiply by scalars. In fact, even more, you can multiply the vectors themselves, right? It's what we call the dot product, right? So there are two things that we're going to learn today. Well, especially I will tell you exactly how they operate in geometry. And the first one will be the dot product. But you already know some of the properties, which is denoted by u dot v. And the other one will be the cross product, which you know from calculus 3, I think, or even from some linear algebra, which is u cross v, right? Okay. All right, now let me define. So the dot product will be nothing else, and I'll define both of them at the same time, and you'll see there'll be a relationship between them, and then we will talk about their applications in geometry. The dot product will be nothing else than just, by the definition, the magnitude of u times the magnitude of v, and something appears here will be the cosine of the angles between them. Okay, let me put it like this. The angle between u and v. So that's the definition. I'm sure you already know. And you'll see in geometry how we apply this dot product. And now the cross product, well, it will be, for example, in 3 dimensions, well, if we, this will be a little bit, I wouldn't say more complicated to define, but for example, in 3 dimensions, because we're interested in that, this will be nothing else than just the determinant of, I'll have these unit vectors I, J, K, if you remember them, and I hope you will. And I will define, okay, in 3 dimensions, U is defined as U1, U2, U3, and V is defined as V1, V2, V3. So here we will put the components of U, will be U1, U2, U3, and this is V1, V2, V3. So this is the determinant of this, and if we expand this, we'll have the following. We'll have these determinants, U2, U3, V2, V3 times I, right? Keep in mind that this I, J, K are these unit vectors. 3-dimensional unit vectors, right? You'll remember them. And in the case of a 2-dimension, you have I and J. They're just the vectors of magnitude 1. Anyway, plus, okay. Okay, let me write here again. U cross V, this is I, J, K. Because at some point we will use this. You'll see where it comes from. V1, V2, V3. So this is U2, U3, V2, V3 times I plus the determinant of U1, U3, V1, V3 times J plus, and now the last one will be what? U1, U2, V1, V2 times K. Anyway, and you expand this, you know how to compute the determinants and so on. But there is an important property here, which says the following, that if we want to compute the magnitude of U cross V, this will be nothing else than just the magnitude of U times the magnitude of V times the sinus of the angles between them. In fact, okay, sine of the angle is between U and V. That's a very important property of the cross product. And of course, you know, at this point, if you subtract by 1/2, right, this will be nothing else than the area of the, if we have 3 points, you will see that this will be nothing else by the cross product of 2 vectors will be nothing else than just 1/2 times the area of the triangle. Anyway, that was the important property of, and of course, you know the properties of the dot product. I'm not going to go into this, and you know how it is defined and everything. You know it's positive, definite, and so on. The only thing I would say it's for the cross product. So let me. So an important. It's okay. Important properties. Of the cross product that I would like to remind, and I don't think these are done in any Calc 3. Well, this thing, you know that, for example, for the dot product, we know that is commutative, right? You know that U dot V is the same as V dot U. Well, not in this case, but also one thing I'd like to say, when you dot U with U, you remember it's always non-negative, right? Here, when you cross u with u, guess what? You'll get a zero vector. When you dot u with u, you'll get something, you'll get a scalar, but it will be something non-negative. Here it's a vector and it's actually zero. And also the thing is, okay, so for the dot product, okay, let me remind you that u dot u will always be non-negative. When, for example, I cross u with v, this is not, it's going to be anti-commutative. V cross u. Here, let me remind you that u dot v is the same as v dot u. So you don't have any problems. And now the third one, for example, when we have some kind of distributivity, let's say, when I cross u with, let's say, v plus w, right? Well, here is going to happen the following. So we'll have u cross v plus u cross w, right? And also, there will be a fourth property which will relate the cross product with the, in fact, okay, let me say this. It will relate the cross product with the dot product, and this will be given by the following. So if I have, if I have u cross v cross w, you see, I'm just crossing all three of them. This will be nothing else than just, guess what? It will be w dot u, right, dot v, right, minus v dot u dot w. So we're going to relate these. And now the fifth one will be very important, will be what we call the Jacobi's identity, will be A cross B. Oh my God, I'm always with A's. U cross V cross W. And now if I add with V cross W cross U, and as you can imagine, if I add this with W cross cross U cross V, and this will give me always the zero vector. And this is what we call the Jacobi's identity. In fact, this is much more general than this. And now we can relate the magnitude of the cross product, and I'll put it like this: U cross V. The magnitude of this will be nothing else than just the magnitude of U and the magnitude of V, and each one of them is squared, minus the dot product between them squared. Well, that's one way to relate, and here is a square, sorry. That's one way to relate this. These are very easy to prove, it's just applying the definition. But anyway, this is how we operate when you cross vectors, and you will see how important this is in geometry, for example, when I would like to. And now, I would like to say a few things. So how do we apply these things in geometry? And here is a story. I'm just gonna tell you, well, I'm gonna run through things. I don't know, hope I'm gonna be finishing fast enough. There is one thing, so applications in geometry. That's what we're interested in. And now what I want to do is the following. So I told you that there are vectors, right? And let me draw a picture again. And suppose I have a point here, let's say M. Of course, this will have some coordinates, but I can always draw this here, and this will be nothing else than just this vector OM, right? This is the origin. Also, there will be some operations that this vector will satisfy, right? For example, I would like to see what happens if I have a segment, right? Okay, let me just tell you. So this is a vector in the plane. And now, well, we can for example, what if we have the following? So let's suppose I have a segment AB, and here I have this point M. So such that AM over MB is this K. And let's just say K is positive, right? I don't want M to be outside this segment. I want this guy inside. And I have this, okay, let me write this here. I have this point O here. So I know that AM over MB is K. And I have this point and I want to express my vector OM in terms of these two vectors here. Well, there is one way to do it. We're always going to have that OM vector, and this will be the most basic and the most important relation. OM vector will always be OA vector plus K times OB vector over 1 plus K. So I can always express this in this way, right? For example, if, if M is the midpoint of AB, well, guess what? Then K will be 1. So this implies that OM vector is nothing else than just 1/2 times OA vector plus OB vector, right? So this is the relation you need to know, this guy here. Well, how are we going to prove this? Well, it's not that hard. There will be another thing that you need to know. It can be derived immediately, but I'm not going to go into the proof of this since I'm not the triangle rule, which is due to the French mathematician Charles. And this says the following. So let me draw the triangle here. This is A, B, C. And I'm going to start from A, go from B to C. Well, it's the same thing as saying that, so if I go like this, it's the same as going from A to C. In other words, AB vector, keep in mind that for vectors, it's very important the direction, right? The orientation. So if I start from here, I go all the way from here, and then I go from here to here, is the same as going from here to here. That's the triangle rule. AB plus BC vector is the same as AC vector. Keep this in mind. This is the golden rule. And guess what? When you look at this triangle here, OAB, if you apply the triangle rule in both of these triangles, OA vector plus AM vector is the same as OM vector. But on the other hand, OM vector plus MB vector is the same as OB vector. And then you play around and you know that the ratio is that. You can express this. You'll get exactly this relation. But anyway, I'm not going to go into the details of this, so you already know. Okay, this is the most important thing. And like I said, when M is in the midpoint, when M is something, whatever. But now there'll be what we call this lemma, a very important lemma. Which says the following: if I have a triangle ABC and M, okay, with G is its centroid or center of mass, and we've talked about this, we know what centroid means. This is the meeting point of all the medians in the triangle. Then for any point M in the plane, we have, and this is a very important relation, a MA vector plus MB vector plus MC vector will always be 3 times MC vector. Wow, that's amazing. This is, I think, is due to Leibniz at this point. This is what you need to know. And in fact, maybe I should do the proof of this, because this is important in applications on how to see how to solve different problems when you. So let me put M here, right? And let me draw the medians. This will be AA1. Let's say this is BB1. And this is CC1. And they will meet at this point G. Right? This is the centroid or the center of mass. Okay? And now what I'm trying to prove, well, let me put this point here, M. Let's put it somewhere here so you can see it better. Okay. Keep in mind that I'm trying to express this guy here, right? This guy here, and also this guy here, in terms of this guy here. You see? Look at this picture. Well, this will follow easily if we apply this lemma. We want to, you see this here. And let me show you how we're going to apply. Look at this. Let's look in the triangle. So it's very important to look at some triangles. Okay, this is not a straight line, but imagine it's a straight line. Well, let's look in this triangle, MA1. Keep in mind that this centroid has this property that is the distance from the base. It's 1/3 from the base, distance from the base, and 2/3 from the vertex, right? Keep that in mind. Do you know this? Did you know this before? Oh, yes, but what about you? Did you guys learn this in high school? Actually, I'm curious if you learned this in high school. this was when we talked about geometry back in the days. Well, from what I see, Nadia has heard of this, and in the first thing that we need to know, even before high school. But anyway, let's say in high school, freshman year high school, this is the most important property for the centroid. So this is what we learned. One of the very first things about the centroid of a triangle. But anyway, so in this triangle, we know what? That AG, since over A1G will be what? What is the ratio of this? Since I said that this is 1/3 from the base and 2/3 from the vertex, this implies that AG over A1G will be what? Can you tell me? What is the ratio of this? So once again, this is 1/3 from the base, right? And 2/3 from the vertex. So this means that what? AG over A1G will be 2. Exactly, 2. All right, and now look at this. Let me draw the picture again. So I want you to, and I'm going to draw it in this way. So I have my point M here. This time I have my point G here. And this I'll have A and A1. And look here what I'm trying to compute this guy. In terms of these, oh my God. In terms of these and these. And look here. So applying that previous lemma, it follows that mg vector will be what? Will be ma vector plus k, which in our case will be 2 times ma1 vector over 1 plus 2, which is 3. Or equivalently, we have a 3mg vector is nothing else than just ma vector plus 2 ma1 vector. All right, perfect. And now I'm trying to look for some information about this guy here. So maybe I should write this in a certain way. Now let me look in what triangle, because I want to obtain this information. Look, I'm looking in this triangle MBC. So this was, now I'm looking at the triangle MBC, and let me draw the picture again. Look, so BC, now I have A1 here, and here I have the point M somewhere here. And again, I'm trying to express this. All right, what is A1 here? A1 is the midpoint of this, right? Is the midpoint of, so the ratio BA1, so in this triangle, BA1 over A1C will be what? Can you tell me? What is the ratio? It's 1. This is the midpoint. So it follows what? It follows that MA1 vector is MB vector plus 1 times MC vector. So it's nothing else than just 1/2 times this. Well, guess what? We have these two relations here. Look at them. You see them here? And now I'm just going to plug in MA1 here. So finally, we're going to get the following. Finally, we have that 3mg vector, or maybe I could look here, even here I could look. we have 3mg vector, so it's ma vector plus 2ma1 vector, but this guy here is nothing else than just ma vector plus plus 1/2 times mv vector plus mc vector. Okay, that's beautiful. Wait. Okay, it's 2 times this. Yep. Forgot about the 2, so which is equivalent with 3mg vector is ma vector plus mv vector plus mc vector. And that's what we wanted to prove. You see, this is a very important relation. Keep this in mind, because now it's for it holds true for any point m in the plane, and now I can basically take m to be the circumcenter. I can take m to be some of the important points in the triangle, right? Let's see some particular cases. For example, let's take M to be O. So O is the circumcenter. So we'll have what? We'll have that OA vector. Let me write it with OA vector plus OB vector plus OC vector is 3OG vector. Sometimes when we do problems, it's very important to work with this relation, because you can assume that the origin is at the circumcenter. But anyway, what if M is G? Is in fact the centroid, because we can we can take M to be centroid. It's any point in the plane, so I have no problems with that. So it will give us what? Can you tell me? If I put M to be G here, will give us what? 3GG vector. But what is the GG vector? Can you tell me? It will always be the 0 vector. This guy is 0. So it's the vector that doesn't go anywhere. So in other words, you'll have, okay, let me put it like this. This is the 0 vector. Ouch. This will be nothing else than just the 0 vector. Right? And the third one, what if we put here, okay, I actually have 4 points. M, let's say, is the orthocenter. So we will have what? We will have that 3HG vector will be HA vector plus HB vector plus HC vector. Okay. And now the fourth one, well, let's say M is I, which I is the incenter, right? You know what the incenter is the intersection point of the bisectors. And we will have this important relation. 3ij vector is AI vector, IB vector plus IC vector. Again, well, guess what? You can play around with these, and you'll see. Also, there is one thing that I would like to mention. Fifth one, maybe I shouldn't say Sylvester relation. which says the following: if the origin, and this is a very important assumption, if the origin is set at the circumcenter of the triangle of circumcenter, let's say O, of the triangle ABC, then we have this, what we call Sylvester inequality, which says that OA vector plus OB vector plus OC vector will always be OH vector. And from here, for all these relations, it will follow immediately that the points H, G, and O are on the same line, which we call the Euler line. In fact, we can prove that. Okay, let me also, one can show that, and I'll leave it to you as an exercise because I don't want to spend too much time with this. Whoa. One can show that HG vector is the same as 2GO vector. Anyway, so it will imply that HG and O, HG and O are on the same line. And I'm sure you will look at the video from yesterday, from very late last night. We used this in one of the problems, in one of the Putnam problems. This is Euler's line. And I'll suggest you watch it because the problems are simple, but they have something in there. Okay. Oh my God, there's so much to do. All right, you see, you can mimic all this here. For example, now, what if I want to, instead of using G, maybe I would like to use the incenter, for example. So again, a similar lemma. And I'm just going to state it, and I'm going to leave it to you to prove it because I don't want to lose time. I'm just going to tell you how. Well, you can take it as an exercise, which says the following. Let's say I have a triangle ABC, and I is its in center, right? And then the same thing will hold true, right? Then for any point M in the plane, we have, let me just, so it will be A times MA vector plus B times BMB vector plus C times MC vector, which will be A plus B plus C times MI vector. Wow. And let me explain this. So we have this equality, which will be similar. And you will, once I draw the picture, you see exactly what do I mean by that. A, B, C, right? Again, this will be the bisector this time. This will be, let's say, AD. And here I'll have some point the incenter. And you know the bisector theorem. You know how to, you know that, let me denote this. So this is B, this is C, and this is A. You know the bisector theorem, which says that BD over DC is C over B. Well, you can play around with these. And then from any point M, you just do the same thing. You mimic the exact same technique as we did for the previous one. Again, you look at these two triangles. You look first at the triangle MAD. you know that you can compute mi from there, and you know ai over ed, you know how to compute this ratio. Actually, it's not hard. Anyway, I'll leave it to you. But this is how we prove, well, this is just two of them. There are plenty of others. But there are some other things that, and what we call Leibniz inequality. And this will be, if we erase everything, if we square everything, so if we square ma vector plus mb vector plus mc vector, right? If we square this equals 3mg vector, well, we obtain this relation, which will be ma squared, so no more vectors, mb squared plus mc squared. I'm going to write them like this so that you can see, is nothing else than ga squared plus gb squared plus gc squared plus 3mg squared. And the way we do this is the following, in the following way. Well, for example, just square this, and when you square it, you have ma squared plus mb squared plus mc squared. You already have them, but you also have the two times the dot product between them, right? ma and mb, and then you apply the cosine law and so on, right? All right, but now I want to show you an example of how to apply. So let's do problems now. Problem 1, which is a classical problem. I want you to see exactly how we apply the properties of the dot product. So and I'm going to think of an example. If a triangle, in triangle ABC, let's say the medians, let's say B prime and C prime are perpendicular, and we'll see what the, because one of the problems from the worksheet says this. And in fact, one of the Putnam problems says, even one of the recent Putnam problems, I think last year or 2 years ago, said that, well, if the in-center, if the segment IG, where I is the in-center, G is the centroid, is parallel to one of the sides of the triangle, something happens. Well, in one of the problems that I will assign and I will solve in the recitation will be what happens if IG is perpendicular to BC, for example. And now I would like to see what happens if these two are perpendicular. Then are perpendicular, okay. Oops. Show that b squared plus c squared equals 5a squared. Let me draw the triangle. Okay, so these two medians here, let me be, this one goes like this. Well, it's more like an altitude. Wow, that's actually a straight line. That's no, that's not okay. I don't want to draw it like a straight line too much. So let's say it's here, B prime. And okay, I'm going to draw this one here. And we know that this is perpendicular to this. Well, it doesn't look that way, but anyway, let's assume that. And this is A, this is B, and this is C, as we know, right? The standard notation for the triangle. Well, guess what? We apply the properties of the dot product. When you hear the word perpendicular, you always think of this. Do you remember? Well, there was this property which follows immediately from the definition. If two vectors are perpendicular, what happens to their dot product? Do you remember that? Exactly, their dot product is 0. Well. In this case, what are my two vectors? Well, is this vector here, BB prime, which is this guy here, and is this vector here, CC prime, which is this guy here. So these two vectors are perpendicular. What does this mean? This means that their dot product, let's write this, in fact, almost BB prime is perpendicular to CC prime if and only if BB prime vector dot CC prime vector is a 0, right? Okay, that's what you need to know. And now let's express each one of them. Can you tell me how can we express a BB vector? Well, since B is the midpoint, what is BB prime vector? In terms of BA and BC, since it's the midpoint, it's 1/2 times BA vector plus BC vector. And CC prime vector is 1/2 times CA vector plus CB vector. Pay attention to the orientation here because I'm starting from C and I'm going, it's not, you see, CB vector is not the same as BC vector, it's minus BC vector. Keep that in mind. The orientation is very important. And now let's dot these two. So this implies that this implies what? It implies that the BA vector plus BC vector times, well, doesn't matter, 1/2 CA vector plus CB vector is 0, which will be equivalent with, and now let's do all these computations here. This will be BA vector times CA vector plus BA vector times CB vector plus BC vector times CA vector, oh my, plus BC vector times CB vector. Okay, this will be 0. Well, let's see. Let's look at some of these guys here. BA vector times CA vector. What is this? Let's write this one. This is what? Pay attention. No, it's not CB. And you mean it's CB. I agree. Or maybe let me just write it in this way so that you can see it. It's BA times CA, right? Like this, times the cosine of the angle between them. Yes, exactly. Between BA vector and CA vector. So this will be exactly, so BA, which is C, CA is B, times this cosine of the angle between these vectors, right? Whatever, that angle. But what is the cosine of this angle? That is the question. How can we express this cosine of this guy here? There was this theorem that I gave you anyway. It's called the cosine law. So this can be expressed by the cosine law. Well, in fact, can you tell me what this is the cosine of what? Between these vectors, BA and CA. BA and CA is cosine. So BA and CA is cosine of A, right? Of the angle A. So let's write all this together. So finally, let's write everything up. So this is just the first one. So we have, this is equivalent with with what? With CB times cosine of A plus, now let's see the second one, BA times BA vector times CB vector, BA times CB. So it will be C times A, right? So wait. This is what it's CB and CA. Okay, it's BA plus CB. So it will have okay, let me look, BA and CB. Yeah, so it will be something like, and it will have minus there. Anyway, I'm just gonna write it directly, and you'll figure it out, where minus AB cosine C minus, let's see the list, this one, minus AC cosine B. And the last one is, well, is negative, right? A squared. Because the dot product with itself is the magnitude, but the orientation is different. Anyway, so this is equal to 0. And this will be equivalent. I'll leave it to you to figure this one out. It's quite easy, but I don't want to lose time right now. So this will be, well, at some point there will be, well, I should say this, a trigonometric identity, which is important for you to use, which says the following: B cos C plus C cosine of B is A, and the analogs. So using this, we have, and now let's see. So A is that, oh my. Anyway, at some point you'll have after some computations, I think I've done some computations here. All right, so this would be something like this. So it's BC cosine of A plus, actually minus, sorry, A squared minus B squared equals 0. All right, yeah. So this would be equivalent with BC cosine of A, which is A squared plus B squared. But now you can apply the cosine law. So this guy, you can express it, but cosine of A is just computations now. It's B squared plus C squared minus A squared over 2BC, and then we have what? It will be it will be B squared plus C squared minus A squared is equal to 2 times A squared plus B squared. And from here you can infer that what? That did I forget anything here? I think I forgot something. Because I'm really anyway, at some point you'll get, just forgive my computations, you'll get this. So I'm going to say it, I did something wrong. Check the computations. All right, now I want to do another problem. Let's say problem 2, and this will be an old Putnam problem, but it's, you'll see I will get stuck at some point. I want to do this problem. So this was a Putnam A3, and you'll see, I will show you a new technique here, in 1962. All right, the problem says the following. All right. Well, it would be better if I draw a picture, but let's write it. In a triangle, ABC. Okay, I'm just going to write it the way it was stated in the exam. In the Euclidean plane, right? Let A prime be a point on the segment from B to C. B prime be a point on the segment from C to A, and as you can guess, and C prime be a point on the segment from A to B. Okay, such that something happens here. AB prime over B prime C is the same as BC prime over C prime A, and CA prime over A prime B is K, where K is a positive constant. Okay, and let delta be the triangle, right, formed by parts of the segments obtained by joining A and A prime, B and B prime, and C and C prime. Okay, prove that. My God, this statement is quite long. Prove that. Okay, prove that the areas of the triangles delta and ABC are in the ratio K minus 1 squared over K squared plus K plus 1. That is the ratio. Okay, that's the statement. Look at it. Oh my, you cannot even. That's the statement of the problem. It's quite long, but I think if we draw a picture, everything will become much clearer. And let's do that. Okay, here is the picture. This is the triangle. Oh my goodness. ABC, and I have these points here. Let's say I have A prime somewhere here, B prime somewhere here, C prime somewhere here, right? So these two will meet 2 by 2, right? They will meet at these points. Let's just say here it's P, Here is Q, and here is R. And keep in mind that I'm interested in the area of this guy here. That is the area. So delta, this is delta. The area of the triangle PQR. So in other words, we need to show that the area of the triangle PQR over the area of the triangle ABC is that ratio over there. It's k minus 1 squared over k squared plus k plus 1. Right? That's what we need to show. Well, guess what? That's why I want to do this problem, because you'll see at some point we'll get stuck. But anyway, let's look at it. The question is, how can we use vectors to show this? Well, you can do it without vectors too. So the question is, how do we use vectors to show this? Well. Let's see. Well, to use vectors, I need to get some information about the PR vector, PQ vector, or Q vector, right? Or at least about two of them, so that I can apply the cross product. Okay. Actually, there will be another Putnam problem, which probably I'm going to leave it for the recitation, where we will actually use this. But I wanted to do this problem because we'll have problems in using the cross product of vectors. But anyway, let's not get there yet. We need to look at this picture very, 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 very carefully. So I need some information about these guys here. Look at this guy. Maybe this guy. Maybe this guy here. So let me set the origin at some point. Let's say, let's set up the origin of the triangle of the entire configuration. In fact, of our configuration at O, right? O is a circumcenter. All right, great. So I like to express all vectors in terms of this. So let's say I have this point O here. Let me just put another color. Okay, I'm going to use this color for the first time, O. And I'm going to write all these vectors, OP, OQ, and OR. And I'm going to write them in terms of my of OA, OB, and OC. Right? That's the main goal. So I like to do that. Okay, so how should we do this? And here comes the, so I need to know some information about the ratio. So let me look at this triangle. Look here. Well, this is a bit the tricky part. I want to look at this triangle here. So I want to look at this triangle ABB prime. Right? So this triangle ABB prime has this guy, look at, well, you have to turn upside down the picture to look at this guy. It's C, P, and C prime with the transversal C, P, C prime, right? And now guess what I'm going to apply? Well, since this is the transversal, right? We will apply what? Menelaus theorem. Right? Oh my. And now let's see which one is outside. So it will be, you see the point C is outside the triangle. So it will be B prime C. And we have, so just look at the picture. Let's look at the picture together. Look at the triangle. The triangle is B prime A, B. The point C prime and P are on the side, are inside, but the point C is outside, right, of the triangle. So this implies that B prime C over B prime C over CA times, so over CA, and then we're at A, times AC prime over C prime B, or BC prime, it doesn't matter since we're not talking about vectors yet, and times BP times PB prime. PB prime. This product is 1. Is it clear how I apply Menelaus theorem here for everybody? Jack, is it clear?
Yeah.
Okay, great. So keep in mind the transversal, and keep in mind which point is outside the triangle. And this is how you apply it. And you imagine that it's kind of inside. This C, imagine that it's inside. So that's why you need to start from there. Anyway, all right. And now let's look at this. So we know a bunch of them. So from here, anyway, I'm just gonna leave it to you as an exercise to show that from here, since I've done this problem and I've done the computations, from here it will follow that I'll find this guy here. So it will follow that BP over BB prime is nothing else than just K times 1 plus K. So I know this, right? I'll leave this to you as an exercise too. It's very easy to show. All right, once we figure out this, let's go back at the picture. You see, I know the ratio BP over PB prime. So I can do the same thing for the others, as you can imagine, right? And now I can express my vector OP. You see, I can express my vector OP in terms of what? Of OB vector and OB prime vector. Wow. So let me draw the configuration separately here. Okay. Let me draw this line so that you can see it better. It's B, P, and B prime. B, P, and B prime. And here I have O. I'm trying to express OP vector. So again, I'm going to use that relation that I gave you. I know that BP, keep in mind that BP over PB prime is K times 1 plus K. So this implies that OP vector will be what? Will be OB vector plus K times K plus 1 OB prime vector, everything over 1 plus K times k plus 1. All right, beautiful. But now OB vector I can express, but OB prime vector, sorry, I can express this. Let's look at the picture. OB prime vector is what? Well, well, you see, I can express it if I look at this segment, you see, if I look at here, and if I draw this here, oh my God, the pictures will become like crazy. I can express this, so let me just take the segment again. So I have O here, this is B prime, and B prime is on AC. So again, I can do the same thing. Right? I can do the same thing, and this will give us what? That OB vector is, I know that AB prime over BC prime, or no, BC prime over C, okay. So this will give us what? This will give us that is OA vector plus K times OC vector, everything over 1 plus K. And now I plug this in here, goes here, right? And we obtain the following. So we obtain that OP vector is the same, is, well, at some point after you do the computations and everything and so on, we will get that this is 1 plus 1 over K plus K squared times, this will be the common factor, K times OA vector plus K times OB vector plus, no, this is 1 here, I'm sorry. I'm going to put here 1 and you'll see why, plus K squared times OC vector. Well, and the analogs. Let's write them. OQ vector, which will be 1 over 1 plus K squared times, well, you see these guys, K1 and K squared will just go for, so it will be, here we'll have K squared OA vector plus KOB vector plus 1 times OC vector. And the last one, OR vector, this will be 1 over 1 plus K squared. And now you'll have 1 times OA vector plus K squared times OB vector plus K times OC vector. Okay, so we have this. Now the question is how to compute the area. How can we compute the area of the triangle PQR? That's what I'm interested in. So I know only these vectors. Well, the area, we know there is a formula, the area of the triangle PQR, based on what we have said, this is nothing else than just 1/2 times the magnitude of PR vector cross PQ vector. So we can do this. Well, if you want to do this, I have one thing to say to you, and this one thing is good luck. I tried to do the computations. They were, man, I didn't want to lose any more time. I don't want to say how much time I spent. No, maybe I just did the wrong, because why I would say this, you can write RP vector as, well, using the triangle rule, as OP vector plus minus OR vector. Well, subtract these two, try to cross them, and you see, maybe it will work. Maybe it didn't work out. Well, I didn't want to continue the computations because it's already everything was too heavy and it was a waste of time at some point. But maybe there is something we can do. And anyway, I'll continue with that something in another video when I'll solve, well, that will be the recitation, but I would like to continue with this problem, and then you will see where this approach will actually work when I will solve another problem from the Putnam. Okay, guys, I think now it's a good place to stop at this point. I'll send you an email. By the way, I have an announcement to make. Those of you who are really interested, tomorrow at 5 p.m., Jack would like to present you two Putnam problems. One of them is an A1, which is considered to be the easiest problem, but the other one is an A6. So Jack has some solutions of his own, and he would like to share this with you. I'll send an email about this. He will be the host, the co-host of, what we will call the second recitation. Okay, thank you very much.